Okay, the fourth concept is what is the total force acting on a wire that transport a current I. If I have a wire that is transporting a current I, and the wire have the charges moving, of course, if not, how he will transport a current I, current I, current I. And now, what is the magnetic field that is acting on this current? Well, if there is a magnetic field acting on this current, it's because there is a magnetic field here. Let's say that the magnetic field is here. It's like this, in this direction. So we need to know what is the total force. The total force is the sum of all the forces to every individual particle. So it's the summation of Q sub I, V sub I cross V is the same magnetic field. I suppose that is a uniform magnetic field. So the sum of all the Fi will be this total force. So if you sum all the forces, all the individual forces over all the particles, the force will be I L cross V. And this is the equation that you will find all the times as the total force acting to a conductor, where this is L, this is I entering, this is I going out, and I by L is the vector. If I is 3, the I by L is this vector. If I is 3, it will be 3 times L. So if I is 3 times L. So it's this vector, 3L. 3L cross B, cross the magnetic field that is here, will be the acting force. And to where it will go, 3L cross V, in this case, the force will go in this direction, magnetic force. Okay? If you maintain fixed these points, the wire will do like this, and will be carried by the force. If you maintain fixed this, the force will make a distortion in the length. It will stretch a little bit the conductor. Okay, this is what you have to know. And the fifth concept, key concept here on this chapter, is the torque that is acting on a loop. You have a loop. Through the loop there is a current. In this picture, the current is going counterclockwise. So the current is flowing in the presence of a magnetic field B, that in this case, the magnetic field going perpendicular to the plane XY, so it's going in the theta direction. So through this length, the force is F equal IL cross V. So IL is this vector, IL, the current by the length, and by B, IL cross V will produce a force in this direction. Same thing for this side. It will produce a force in this direction. So you have a pair of forces that will, the sum of the forces is 0, so the object will not be accelerated to anywhere, but it will have a torque, and it will rotate through the axis. To which axis will rotate? It will rotate in this direction, so it will rotate through the y-axis. Through the y-axis it will be the rotation. So there is a torque. If you calculate the torque, I have calculated this in class, the torque will be mu, I have called mu, let's go to call M, cross V, where M is the magnetic dipole and is defined by the intensity by area by the vector U sub n. And what is the vector U sub n? The vector U sub n is the vector that is unitary and is perpendicular to the surface, this surface of the current, this surface. So this is the vector mu. So you take the I, you rotate the current, you make a rotation on the loop, If you make a rotation of the loop, this is the mu. The mu is going like this, or the m, okay, mu, m, whatever. So this is the torque, and the potential energy sub P depends on the angle theta, and is minus m dot V. The dot product of the magnetic dipole, this vector, dot B. Of course, E sub P of theta is minus mb by cosine of theta. This is the two equations that you need to know to solve problems. Let's go to another part. Finally, we are going to see the Hall effects. The Hall effects relate to the following thing. Let's say that you have a plate like this one. It's a metallic plate. The conductor are supposed to be the electrons. So if the current is going in this direction, it's because the electron is going in this direction. Or the positive charge is going in this direction, or the negative charge is going in this direction, and this produces a current in this direction. So, if the current is going in this direction, and the magnetic field is going in this direction, let's say that you have a negative charge. So if you have negative charge, the force will be V cross V. V cross V will pointing down, but because it's negative charge, the force will go in the positive, in going up. So V cross V will go perpendicular to the plane, to this plane. V cross V will go to the perpendicular to the plane going downward, but because they are negative charge, the force will go up. So the force will be created a side in the material of negative charge here. Will be deflected to this direction. This will happen and will happen until the charge that is here, and here will appear positive charge. And this is happening, and meanwhile it's happening, you produce an electrical field. It will happen again that when the electrical field will be enough intense to create a force going down, the charge will pass and deflect it. So we'll go like this and deflect it, because the magnetic force going up will be equal to the electrical field going down. Okay, this is what is happening, and what is related by the magnetic, by the Hall effects is that in some materials, instead of appear the minus here, the minus charge in the upward side and the positive charge, in some material it appeared the positive here and the negative here, and they didn't understand what is happening this. Hall was a student, I think, that he was doing a research on this, and he found this effect, and he was wondering how is possible if the moving charge are negative that this will be positive. This is happening when the material is a semiconductor. When the material is a semiconductor, what is moving is a positive charge, or is a hole, is the empty space of a negative charge. And that's all what you have to know, okay? This condition is happening when there is an equilibrium between the two forces. When there is an equilibrium between the two forces, this equation is happening. And to obtain this equation, you see the picture here, and you know that the density of current is NQV. In this case, the only component of density of current is in the x direction, so it will be NQ by V sub x. In the case that you arrive to an equilibrium where the magnetic force will be in the zeta direction and will have the magnitude Q by the velocity Vx by the magnetic field Vy, and the force going down due to the electrical field that produce this charge. Well, in this case, the electrical force will go up. Well, no, it will go down because it's a negative charge. When these two forces, the magnetic force and the electrical force, are in equilibrium, these forces are equal, both of them. So one is going up, the other one is going downwards, and the total force should be zero. And in this case, the velocity Vx, it will be, you look for this minus sign, it will be easy to find E zeta divided by Vy. So the J will be nq by Vx, but the Vx will be E zeta divided by Vy. So nq is zeta divided by Vy minus, so the nq, it will be gx Vy E zeta minus. And this is the quantity that in some problems they ask you by the number of charge per unit of volume by the individual charge, the total charge per unit of volume, the density of charge. This is the density of charge per unit of volume, N by Q. That's all.